First of all, I'd like to thank GSMA and CTIA for, again, putting on a spectacular show. Very informative, very enjoyable, actually, also. So, great job there. Thanks, Sylvia. Really appreciate it. And I really want to thank everybody who's in the audience here at 2 p.m. on Friday, the last day of the show. So it's incumbent upon us to put on some really spectacular demos. So let's hope the demo gods are good to us today. This worked spectacular yesterday, and I think it's pretty mind-blowing when you see it. Maybe a little introduction. I'm Brian Deutsch, as Sylvia said. So I'm the CEO of Pivotal Comware. We're a company up in Bellevue, Washington. We're the creator. We've actually taken advantage of a breakthrough in electromagnetic physics called metamaterials, and we've created a technology called holographic beamforming. It sounds rather Star Wars-like, but what it does is it allows us to create, in essence, a software-defined antenna. And unlike predecessor legacy technologies like phased arrays or MIMO, massive MIMO, what it does is gives us advantages in terms of cost and size and weight and power consumption. Some of these, many multiples, some of them orders of magnitude improvements in these various parameters. And what we do with this is it allows us to formulate a software-defined antenna, as I said, and then take that into the field and help carriers, help mobile network operators better manage their spectrum, optimize things like coverage, capacity, and throughput, and maximize spectral efficiency. So we've been at this for about a little over 2.5 years, but even predecessor to that, we were incubating inside something called Invention Science Fund out of Bellevue, and it's a great idea. We take some scientists, some technologists, some marketing people, some entrepreneurs, and we put them all together and we find a great idea, or we find some raw science and we take a deep science bet on it. And then we take several shots on goal using that same scientific platform, that same portfolio of patents and intellectual property. So Pivotal Comware is actually the fourth spun out from a commercialization center, including one in satellite, one in radar, one in security imaging, and then Pivotal Comware is the masters of terrestrial communications. So our domain is the core of the Earth to the mesosphere. Our investor base is actually a who's who of some corporate and strategic and also private equity investors, but our most passionate investor, our lead investor, our most important, our most valuable player is Bill Gates. And Bill shares our passion for kind of the art and science, but also the promise of what metamaterials and holographic beamforming really hold to the communications markets, to the radar markets, to also wireless power, all sorts of markets that we can promulgate using that. And on those markets for terrestrial communications, we started in business looking at things like access and motion. So if you have a beamformer, this is an example of a millimeter wave beamformer. So it looks like just a printed circuit board. So this takes the place of those phased arrays that are super heavy, super power hungry, cost thousands and thousands of dollars, with something that's a monolithic printed circuit board. And I'll explain why we call it holographic beamforming in a minute, and that plays into really kind of the efficiency and efficaciousness of this antenna. So we looked at markets that we called access and motion, so train to trackside, air to ground, ship to shore, things like that, where you needed a moving beam in order to train all the energy, all the radio energy on a moving target. And we've been very successful in those markets. We actually spun the company out without raising any money because they had customers in tow, which was spectacular. I've done quite a few of these. That was the first. I've never done that. And then we went and raised a bunch of money. But nevertheless, we moved on from those access and motion systems, although we still do those, and then government systems. It didn't take long for the government to start knocking on our door and say, hey, can you hang this from a quadcopter and do things in battle theaters with it? And of course we can, and it's spectacular. But our wheelhouse, why we're here today, and what we're most proud of is what we do in radio access network and broadband wireless transport. And so those backhaul, front haul, wireless backhaul, front haul. In fact, this is a 39 gigahertz antenna that goes into a product we call fast haul, I'm sorry. And the fast haul is for those, lack and the dearth of dark fiber connections to those CRAN-based small cells that are sitting out there without any dark fiber to plug in. Sometimes it's only across the street, sometimes it's half a kilometer away, but we need some way to bridge that SIP rate wirelessly, and we've done that. We have our own modem teams, our own radio teams, and we bring those to bear for this product, and we've done really well as far as that's concerned. What we're going to show today is something that's much more near and dear to what it seems that this entire conference is about, and that's 5G and some of the challenges that were presented for us to solve by some of the world's biggest network operators for 5G. First, real quick, why do we call it holographic beamforming? Because again, the art and science behind this, I had mentioned something called metamaterials, which you can actually go and Google that and look into the science behind it. Why we call it holographic beamforming is because very much like holography, where a laser or coherent light or some type of source is actually pushed through a holographic plate, and then the interference between those two things creates a hologram. It's very much holograms light. Radio waves are light. They're all electromagnetic waves, they're just a different frequency. So we applied that same principle basically to this highly oversampled array of elements. And then all we had to do was figure out, okay, well, what's the analogy for that holographic surface? And we did, we figured out what that was. And I'm gonna do engineer speak here, and pardon me, because I don't know another way to say this, but it was really just the surface impedance modulation of the top of this antenna that we had to modulate. And so we formed that hologram on this surface, and the interference between that and the radio signal that's coming in is the beam. We can form beams. We can put beams on the sides of antennas on the sides of building and bifurcate the beams so at 6 a.m. to 9 a.m. we're actually flooding the pedestrian corridors in the street with radio signals. And at 9 a.m. we can move that signal up into the buildings so that we can wash the buildings with radio signals. And then of course back down for the afternoon commute and so on and so forth. We call that directivity on demand, and it's something we're really proud of. And we're working actually more and more towards machine learning and intelligent beam management service so that we can continue to help operators understand how best to manifest those radio waves into spatial corridors and get the most out of them. Okay, so we're going to talk a little bit about our demo now. If we could switch up to show live feed here. So with the help of Mirsad and Ray and our friends from a galaxy far, far away up here, what we're going to show you is a manifestation of a product we call Echo. So this is a fairly well-known setup, especially in your fixed wireless world, where you have a base station, and then over here you have a house. And so you have a piece of CPE inside the house. This house is rather difficult to get into because this is all super low E glass, low emissions. So that's going to cause a lot of problems for us. There's a couple of challenges that faced us in getting to the promise of 5G, okay, is that promise of high throughput, low latency, millions of devices. And my colleagues here, I believe, are going to show you these higher level IoT ecosystem applications. What we're showing you is really the baseline of, can we make this work? Can we get this done? Can we get that signal into the house so that these people can enjoy, movies on demand and all sorts of other things? We've actually loaded this. There's a radio on this end, there's a radio on this end for the tech geeks. And so it's 100 megahertz channel, I believe, that we have going over here. This is a 4K or 8K movie, so that's not much of a load for that channel. So we stuffed a bunch of fake traffic in there to make it a lot harder. And you'll see why we've done that, so that we can actually simulate the real world a little better. What you're actually going to look at, though, is the original prototype of what's become now our Echo 5G repeater. This is an on-the-glass repeater, and the concept here is that the outdoor unit is completely wireless. So the outdoor unit is powered inductively by the indoor unit, so that it's a self-install. This was really important. One of the challenges that we were presented with earlier this year was unit economics. And unit economics also means self-install. So we had to make sure that we nailed those unit economics. The other one was that we could extend the range so that one base station could serve all the way a kilometer away. They were having a hard time getting 10 houses, 20 or 30 houses, and we're getting a kilometer away and pushing a gigabit through. We've tested this in the field and gone half a kilometer from absolute zero throughput to 1.3 gigabits in an actual live field trial, carrier field trial. So those were kind of the challenges that were presented before us, and this is our solution. So what we're showing here now is a situation where we have unfettered access to the inside of the house, and so there's no window. It's completely open. Somebody opened the door and let the signal in to the CPU, and now Mersad's can actually show you what happens when you put two pane, and they, by the way, in places like Switzerland, they have three pane low E glass, just to make it even harder. So this is a kind of problem that you'll face, and you can see, that's not Luke Skywalker, that's the other guy, right? Yeah. It was probably the worst Star Wars movie. But anyway, so you can see he's stuck in motion here. So what we're going to do now is show you when we take this off, of course, the video is going to start playing again because we've opened the door. But now we're going to put our echo unit on. And again, this was one of the original prototypes we used in the field. And we're going to put echo on, and it's going to actually go track and find that signal, hopefully. It's going to go try and track that signal, and it's going to amplify it and push it through the glass. So it's going to take what used to be 40 decibels of loss, and then it's going to turn that into the gain of the antenna, which is about 20 dB, and it's going to master the reflection off the glass and ameliorate that, basically take it away and turn that into a positive, and then it's going to push the signal through. So echo's off, and now let's turn echo on. Let's cross our fingers, and there it is. Okay, so come on. Let's start fighting. There we go. And so the speedometer is actually indicative of the number of bits going through. The video player does have to queue up, so that's what you're seeing there. And so that's with echo on. And let's go ahead and shut it off again just so we can show them that this isn't all hocus pocus. And then back on again. Okay, so we've conquered low E glass, that's great. Straight on, that's a straight shot. There's another problem though, so if you hit, how many times are you gonna be right straight across the street from your base station? Almost never. So now you have another problem, which is just as big, and it's the angle of incidence that you hit the glass. So you're gonna hit this glass at 40, 50, 60, 70, even 80 degrees. And when you do that, most of the energy is gonna bounce off. So we're gonna take that 80% loss and turn it into 20 dB gain. So if we can show that in motion. Let's see if we can do this. This is the tricky one here. Okay, so right now the antenna is still pointing forward. So if you could do a little Akin track there to try and get the antenna to point back at. There we go. So now we have the antenna turned, and it's tracking this system over here, the base station, and we're back online. Crank it off again, just so we can show that no hocus pocus here, and then on one more time. And for those of you that are still non-believers, here, I'll take one for the team. There we go. So that's Echo 5G. That's what we can do with holographic beamforming, and a little bit, like I said, a little bit of passion, a little bit of art and science. Is there any questions? I have 3 minutes and 40 seconds left. I don't know if we had any questions. We're in, oh, go ahead, sir. I didn't hear.
We're still using the same receiver inside?
Yeah. Oh yes, it's just a repeater. So it's very low latency. Now what we can also do with these, which I'm glad you prompted me, is these can go out in the field. So if I'm a base station like this one and I'm serving a neighborhood, and all of a sudden there's a cul-de-sac, well, I got to put another base station in over there? Or can I put a reflector in? So we put these echo units back to back. And so we take two holographic beamformers, one on one side, one on the other. One finds the donor, and the second one rounds the corner and can find anybody inside the cul-de-sac or can flood the cul-de-sac. And then we can take them, and because we can go out almost a kilometer, like I said, with these. And then we can actually go from one, the link budget shows we can go to one more. And then from there, we can actually go to a house that's a kilometer away. Now we go 3 kilometers from a base station. So now all of a sudden, you can grow this organic fiber into your neighborhood. So you can put, rather than having, there's one subscriber here, one here, one here, and one here, and all of a sudden I have to put 4 base stations in for 4 subscribers as I build out this neighborhood. Or I could put 1 base station in and shoot, through echo reflectors and relays all around the neighborhood. Is there any other questions?
We don't have a microphone.
I'm sorry? Oh.
Any other questions?
All right. Well, oh, yes, sir.
Are they band specific?
Is it band specific?
Yes, you need a band or
Within reason. So, 28, we could probably do 28 and 24 in one unit. 39 and 24, or 28, no, we couldn't do in the same unit. And, there's some components in there in terms of LNA and PA to push this through, because it's bistatic. It actually, works. That's the beauty of this, by the way. I don't care if it's TF. I don't care if it's NR. This isn't either. This is neither TF nor NR. It's a proprietary protocol that this radio company is using. And so it doesn't really care because it's agnostic to all that. As it pushes it through, which works out really well for upgrades and things like that. We can actually address this, by the way. We put an IoT module in here, so this actually becomes a node on your 4G network. So if you want to update the software or update the Beam catalog, you're able to do that without having to work through the OEM themselves. So it's a part of that disaggregation that everybody's been looking for. Well, thank you very much. Really appreciate it. Again, thanks to everyone, and look forward to next year. Thank you.